Welcome to a crash course in Soft Actor Critic methods. You're going to learn the least painful way to quickly implement the Soft Actor Critic algorithm using Tensorflow2. We're going to implement this and test it on the PyBullet environment, the Inverted Pendulum, because it's relatively quick to compute. It runs pretty fast, so we'll know whether or not we got it right relatively quickly. So what exactly is a Soft Actor Critic algorithm? So this algorithm sets out to address a pretty fundamental issue in deep reinforcement learning, which is how do we use a maximum entropy framework in actor critic methods. We're going to go a little more detail into this in a moment, but that is the basic idea behind what we want to do. So why would this even be something worth considering? Well, as you may be aware, actor critic methods have a number of fundamental limitations, not the least of which is the fact that they have what is called brittle convergence, meaning that they suffer from a high degree of hyperparameter tuning. If you go monkeying around with hyperparameters, the agent breaks and doesn't know what to do in the environment, and so once you find a set of hyperparameters, you really have to stick with them. Worse than that, you have a problem called high sample complexity, which is just a fancy way of saying you need to play a whole bunch of games for the agent to figure out how it works. It's not very efficient for environments in which you have large state spaces and high number of actions in a continuous action space. Worst of all, these two fundamental drawbacks really limit real-world applicability, and is probably one of the big reasons behind why we haven't seen any widespread adoption of deep reinforcement learning in something like, say, robotics. So Soft Actor Critic, as I said, is a maximum entropy framework, and what this means specifically is that the agent is going to maximize both long-term rewards and entropy. Well, what does entropy even mean in this context? Well, if you're not familiar with the concept of entropy, it's strictly speaking a measure of disorder in your system. It stems from statistical physics and thermodynamics. It's basically the log of the multiplicity of your system, the number of ways of arranging the components of your system. What does that mean in the context of deep reinforcement learning? It means the randomness of the actions of your agent. And you might wonder, why would you want to maximize both long-term rewards and randomness of your agent? The reason is that we need to have some degree of random actions to test our model of the world. The agent starts out knowing absolutely nothing about the world, and so should act as randomly as possible, and then as it starts to figure out what actions lead to rewards, it should eventually start to converge on taking mostly those actions, but still spend some time exploring to make sure that there isn't some better action out there. This isn't a totally alien concept to you if you're familiar with Q-learning. There we use what's called epsilon greedy action selection, where some proportion of the time, say 10% of the time, we take a random action no matter what. Even if we know what the best possible action is, we may still take a totally random action simply because you can never be 100% certain that you're right. In this algorithm, we're going to be modeling entropy by reward scaling. So we're going to have a multiplicative factor for our reward, and there's going to be an inverse relationship between our reward scale and the degree of entropy in the system. And you can kind of think of this intuitively because if you increase the scaling on the reward, you're going to increase the contribution of that reward to the cost function, and so you're going to kind of tilt the neural network parameters towards maximizing that reward. Whereas if you lower that parameter, then you're going to lessen the contribution of the signal of the reward to the updates of the neural network, and so decrease its overall importance to the cost function. This algorithm is also going to leverage all the neural networks possible. We're going to have networks for actors, value network, and critic networks. And in particular, we're actually going to have two critic networks, which is going to be an exact analog of the double Q-learning algorithm, as well as twin-delayed deep deterministic policy gradients, another awesome algorithm for continuous action space environments. Please see other videos on this channel if you don't know much about those. I have a multitude of videos covering both of those topics. They also make use of another innovation from Q-learning, which is the use of a target value function. So the idea here is that we're going to be using our value function to track the values of states to tell us which states are valuable, so we can seek out those states again. That's the idea behind reinforcement learning. But the problem is that we're going to be updating that value function with each time step. And so if you're updating it at each time step and using it to evaluate the values of states, then you're really chasing a moving target, and so the algorithm will suffer from instability, and that happens a lot in Q-learning as well. The solution is to have a target value function which is updated only periodically or very slowly. So in Q-learning, we do a periodic update where we just exactly copy the network parameters from one network to another, from the online to the target network. Here we're going to make use of a soft update where it's going to be some kind of moving average of the online and previous values of this target value network. And I'll show you that equation later in this little lecture. So our actor network is going to model both the mean and sigma of a distribution. So this is a probabilistic policy. It is not a deterministic policy like in DDPG. So our actor network is going to output two parameters, a mean and sigma, and then we're going to put that mean and sigma into a normal distribution and sample it to get an action. Now, the original paper used what they call a reparameterization trick, and I will fully admit I'm a little fuzzy on exactly what that means. It kind of sounds like they are sampling some normal distribution and then adding on some additional noise to it. I implement this in what I believe to be a faithful implementation of this in PyTorch, but I'm not going to do it in this tutorial. I think it's a little superfluous, and I'm actually getting, really good results without it, so I'm kind of throwing it away. We do have a special function to enforce action bounds, as well as to calculate the log of the probabilities of taking some actions, because the log of the probability will play a big role in our update rules for our networks, which I'll get to momentarily. And I'll show you that function later on in the lecture as well. Another thing to note is that we can use multiple steps of gradient descent like we do in proximal policy optimization or PPO, but we're not going to do that. We're going to just use one step of atom optimization per time step of the environment. Some other implementation notes: we're going to have a replay buffer based on NumPy arrays. I prefer NumPy arrays. That is by no means the only way to do it. Not even necessarily the best way. It's just my preferred solution. Change that if you want. Now we're going to keep track of the states the agent sees, the actions it took, the rewards it received, the new states it resulted from those actions, as well as the terminal flags from our environment. And the terminal flags are important because we have to use that in the update for our deep neural networks, because when we're evaluating the values of states, we have to take into account whether or not that state was terminal. The reason is that terminal states have no value because the episode is over and no future rewards follow. The value is just the present value of the discounted future rewards. So if the episode is done, it's 0 by default. Now this is the equation I alluded to earlier, where we are calculating the log of the probability of selecting some action given some state. That's what that pi means. It's a probability of selecting an action, which is a continuous parameter given some state. This mu is our actual sample of a distribution with mean and sigma given by our deep neural network. So it is not the output of our deep neural network. It is the sampling of a distribution where the mean and sigma are given by our deep neural network. And another thing to note here is that we are going to have to multiply our action by the max action from the environment. Reason being is that the action is going to be proportional to the tan hyperbolic function, and that is bounded by plus or minus 1, which not all environments are bound by plus or minus 1, so you want to take into account that fact. We don't want to cut off half of our action space arbitrarily. So let's talk about updating our deep neural networks. Our actor network update is pretty straightforward. What we're going to do is sample states from our buffer, but compute new actions. So this is an off-policy learning method where we're going to be using samples generated by one policy to update some newer policy. We're going to stick those states through our actor network and get new actions out on the other end, compute that log prob based on what we saw on the previous slide, and then we're going to subtract off the minimum value of the two critics. So we're going to pass the states sampled from our buffer, the actions computed in our update according to the current values of our actor network, and then take the minimum of the critic evaluation of those state and action pairs. This is kind of the double Q learning rule in action, so that's why I have it as Q min. And the 1 over n sum tells you that we're taking a mean of that quantity, that difference. Our value network update is a little bit more convoluted. So we're going to have 1/2 the mean squared error. That's what the 1 over n and the 1/2 of the difference squared tells you, of the difference between the value function using the current parameters of our value function for the state sampled from our buffer. Again, we're going to subtract off the minimum of the Q values where the actions are chosen according to the new values of our actor network, and we're going to again subtract off that log of pi, where again the actions are computed according to the current values of our actor network. And again, the log is computed according to a couple slides ago. The target value network, on the other hand, doesn't get any gradient descent to determine its new parameters. We're going to be updating its parameters with the following equation. So we're going to take this hyperparameter tau and multiply it by the values of our online value network, given by psi. That's just the symbol for the parameters for our value network. And we're going to add on 1 minus tau, so 0.995, multiplied by the current values of the target value network, take the sum of those two and upload those values to our target value network. And it's a slowly moving average of online and target networks. Our critic network gets a rather interesting update. So here both critics get updated, so there's no minimum operation here. So there's 2 cost functions, one for each critic, and it's just given by the mean squared error of the difference between the output of the critic for the states and actions sampled from the buffer. And we're not calculating new actions here. That is one difference between the update of the critic and the actor and value networks. And we're subtracting off this quantity Q hat, and that is where the actual entropy comes into play. So it is a scaled reward plus the values of the new states according to our target value network. So this is where all the magic of the algorithm happens. That's where the maximum entropy framework comes into play in this one little equation. Kind of neat, huh? So we're going to need a whole bunch of data structures. Class for our replay buffer, again, that'll be NumPy arrays. The actor network gets a class, the critic network gets a class, so does the value network. Our agent gets its own class, and that's going to tie everything together. That'll have functionality for choosing actions, saving models, learning, as well as saving memories. And we will have a main loop to train and evaluate the performance of our agent. Now we're going to need a number of packages. We'll need TensorFlow. I prefer GPU. Obviously, this is a highly computationally expensive algorithm, so if you have the GPU, please use it. We'll need PyBullet for environment, Gym, of course, NumPy, and TensorFlow-probability. That is the only way we can get access to this probability distributions. They're not built into the base TensorFlow package for some reason. Okay, that's it for a mini lecture, your crash course. Now let's go ahead and throw you in the water and start coding. All right, so let's go ahead and get started with our buffer class, and then we'll move on to do our networks and our agent class. So we're going to be using NumPy arrays for our memories, and so NumPy will be our only package dependence for this particular part of the agent. We'll need a max size, input shape, and number of actions as input. We will need to save our max size, and we will also need a mem counter to keep track of the first available memory position. And our agent's memory is represented by NumPy arrays that we will initialize as zeros, in the shape mem size by input shape, where input shape is some tuple or list. We need the new state memory as well. That are the new states that the agent sees as a consequence of the actions it takes in the environment. We need the action memory, and that is in shape mem size by number of actions. Keep in mind, number of actions means number of components to the action. Since these are continuous actions, they will have components along some dimension in action space. It's not an actual number of discrete actions. It's a little bit misaptly named. A reward memory and that's just a vector and an array to keep track of the terminal flags we receive from the environment. And I'll go ahead and say that is type numpy bool. Next, we need a function to store a transition. And if it isn't clear, the reason we need to store the terminal flags is because the value of the terminal state is always 0, because no future rewards follow the terminal state, and so it has no value. So we will need to save all of those parameters in our agent's memory, and we want to know what is the position of the first available memory, and that's given by the modulus of mem counter and mem size. This has the property that when we overwrite the agent's memory, we will go back to the very beginning, so we don't have to worry about going beyond the bounds of our array. So then we just go ahead and save our variables. And terminal memory. And most importantly, we need to increment our memory counter by 1. Next, we need a function to sample our buffer. And I want to make a quick aside here. So in a question in the comment section, someone asked, is there a way to sample memories according to how valuable they were? Our early memories, the agent's acting randomly, doesn't know what it's doing. So what good is it to sample those memories? Isn't it more important to sample memories where we kind of knew what we were doing and had some reasonable model of the environment? And you can do that in something like prioritized experience replay, where you prioritize memories based on their utility. But in this case, we're just doing uniform sampling, so we just take the good with the bad. So we want to know the first available memory, how far we have gone in our memory, and that's given by the minimum of the mem size and the mem counter. That's so that we're not, if we've filled up half of our memory, we don't want to sample the latter half, which is all zeros. We only want to sample the first half, which is filled up with useful transitions. And so then we're going to go ahead and take a batch size of memories from our memory bank and go ahead and dereference them. Sorry, we need an extra space there. And then go ahead and return those states, actions, rewards, new states, and terminal flags. And that is it for our memory buffer class. Next up, we're going to handle our networks for the agent. So the first thing, obviously, we want to do is come up and fix our imports because we're going to need more stuff than just NumPy. We're going to need OS, the base TensorFlow package, Keras, and we will need TensorFlow probability as TFP. Now you will have to install this package separately. It is not included in the base TensorFlow package. So see the TensorFlow documentation if that is something you don't know how to do, but you do need to do that installation separately. So our critic network will derive from keras.model. That gives us access to making use of the gradients and the gradient tape and all the other good stuff that we get from the base class. We will need a number of actions, number of dims, FC1, FC2 dims, a name. So the name is useful for model checkpointing, so we can keep track of which file corresponds to which network. And a directory for saving models. You have to do a make dir on that, otherwise you'll get an error. First thing you want to do is call your superconstructor, save the relevant parameters, One of these days I'm going to shorten this checkpoint dir name, but not today. So then you want to join the checkpoint file name, checkpoint directory, excuse me, with the name and underscore Soft Actor Critic, so that way when we save a bunch of stuff in a single directory, we know which file corresponds to which algorithm. Next, we can define our model. Our first fully connected layer is just a dense layer that has implied input dimensionality and takes FC1 dims as output with a RU activation. Likewise for our second layer. And our final output is single valued with, single node with no activation. So we have to input a state and action to our call function because the critic network evaluates the values of state action pairs. And so the first thing we want to do is pass the concatenated state and action pair through the first fully connected layer. And we want to concatenate along the first axis. And pass that through the second fully connected layer. And pass that through the output layer. And return. Pretty straightforward there. Next, let's handle our value network. And again, that derives from keras.model. We don't have to specify any dimensionality here other than for our first and second fully connected layers. And we want to call our superconstructor again. And if you wanted to get really fancy, you could write a base model, base network class, and then have everything derived from both the, I guess the base model class would derive from the keras model, and then everything that derives from that would derive from the base network class. But that can get kind of messy really quickly. You have to deal with multiple inheritance. Maybe it's not as hard as I initially think it is, but it's an alternative path. It's an alternative way so that you don't have to keep writing like the same stuff over and over again. Because you notice there's a lot of overlap between the code of the networks, so you can fix that with inheritance. And our output is again going to be single valued with no activation. Now, the call function here only takes the current state of the environment as input. The value function is only concerned with the values of states, not state action pairs. Then we just go ahead and pass all of those through and return them. Pretty straightforward. The real difficulty doesn't occur until the actor network and the difficulty will come in the call function as well as the sample normal. So we want to pass in a max action. Am I using that here? Sorry, I always kind of make stuff on the fly, kind of modify stuff on the fly. Yeah, so we do need that. FC1 dims, SE2 dims, a name, number of actions. I'll use 2 by default. Again, that's number of components, and a checkpoint directory. We're going to call our superconstructor and save the relevant parameters. Okay, and then we have our model name. And just as an aside, you can't use name. It's a reserved variable. You can't say self.name equals name because name is reserved by the base class keras.model. So you have to use model name. So we're not going to be using reparameterization, but we will need some noise factor to make sure we don't get something that blows up when we take the log. You'll see what I mean very shortly. Our neural network by now should look pretty familiar. ReLU activations. Here's where things get interesting. We're going to have a mu for our distribution as well as a sigma with no activation. So let's go ahead and handle our call function. So we're going to get our I called it prob here, but I don't know if I like that name now that I'm rewriting it, but I'm going to roll with it. So mu, really that prob is just the input of our first two layers, the pass through the state through the first couple layers. We'll have our sigma, which is a standard deviation of our distribution, and we're going to want to clip this. It may be the case that TensorFlow2 doesn't need it, but when I was coding this up in PyTorch, the distribution would blow up if we had a sigma of 0. It didn't like a 0 standard deviation distribution, which I can understand. I guess that's a Dirac delta function. It's not exactly something that you would encounter every day. And I think the TensorFlow might actually fail a little bit more gracefully than the PyTorch in that respect. But I go ahead and clip it so that it goes between 1 by 10 to the minus 6 and 1. So we're going to constrain the standard deviation here to not be too large. That is something you can optimize on your own. I don't do extensive and detailed studies on all of this stuff. I just get it working, check that it conforms to the specifications laid out in the paper, and then I get something reasonable on the output. But we're not done for the actor network. We have the output of our deep neural network, which is a mean and standard deviation for our distribution. Now we have to sample that distribution to get the actual action for our agent. And I've stuck it on a function called sample normal. And as I stated, we're not going to be doing the reparameterization trick. I show students how to do that in the course, and in fact in my PyTorch video I show you how to do it. PyTorch has a very simple function called rsample that does basically the reparameterization for you. You can implement the code yourself if you really want to be completionist about it, but I'm not bothering here because I do get good results without it. It's kind of like with the DDPG paper where they use the Ornstein-Uhlenbeck noise, and then people that implemented it later kind of threw it away because they're like, wait a second, this is unnecessary complication. That kind of seems to be the case here, where it worked without it and is an unnecessary complication. But I mean, I could always be wrong, but I do get solid results without it. So here we're going to go ahead and instantiate our normal distribution defined by mu and sigma. And our action is going to be, our actions are going to be a sample, probabilities.sample. If you want to do the reparameterization, you would reparameterize it there. And the action is math.tan hyperbolic times max action. That max action takes care of the fact that our environment may have max actions outside of the bounds plus or minus 1, which are of course the bounds of the tan hyperbolic function. So you want to not arbitrarily cut off half of your action space if you don't have to. Our log probs is probabilities probabilities.log_prob of actions, and then go ahead and subtract off math log 1 minus tf.math.pow, action. So we're going to square the action plus self.reparam. I called it noise, didn't I? Self.noise. And so then I have to change it here as well, don't I? Yep. Self.noise plus self.noise. Do I have the right number of parentheses here? Yes, I do. And so since you have a logarithmic function here, you don't want to take the log of 0. That is oftentimes not advisable. So I just add in some really small number to make sure we're taking the log of something finite. So then we're going to go ahead and do a reduce sum on that. Log probs axis equals 1, keep dims equals true, and return the action and log probs. So that wraps up the networks portion of our code. Now we have to handle the agent class, which will tie everything all together. So of course, again, we have to come back up to the top and add in some imports. We're going to need our optimizer. So we'll say from TensorFlow keras optimizers import atom, and I think that's the only other import we will need. And then we come back down here and start our agent class, which derives from nothing. Our initializer is going to take a number of learning rates. Now we're going to use 2 separate learning rates. You could, in principle, use 3, one for the critic, one for the actor, one for the value network. In this case, we're going to use one single learning rate for the actor, and then the the beta learning rate will be for the value and critic networks. Input dims, something like 8. That's just the default for the lunar lander. It's the only default I know off the top of my head. We're going to want to pass in the environment to get some useful information from it. A gamma, the discount factor for our update equation, max size for our memory, 1,000,000 transitions, default value of tau of 0.005, layer 1 size, layer 2 size 256, batch size default 256, and our reward scale default of 2. Let's go ahead and start saving. Our replay buffer, max size, input dims, number of actions, pretty straightforward. Then we're going to go ahead and define our networks. So our max action is going to be the high value of the action space from our environment. We need our first critic. Second critic. And these are, identical in terms of their definitions, except for the name. Because again, when we save files, we want to save separate files for both critics, otherwise we're going to get a mess. Our value network. And our target value. Okay, so now we have to compile our networks. We'll need our critic 1, running rate of beta, our value network, and our target value. Now, of course, the target value network doesn't perform any optimization. We just copy weights using our soft update rule, but it is part of it's just part of the framework that we have to compile the model before we can use it. Our scale factor, and our initial update network parameters, where we're going to do a hard copy of the parameters from the online network to the target value network. The first function I want to handle is the choose action function. Then we'll get to the remember function, the update network parameters, and our save model parameters. Finally, we'll get to the learn function. We'll save the best for last. So we want to convert our state, our observation, to a tensor. And the neural network expects that we will have a batch dimension, so we have to do that. We have to add an extra dimension to get our batch. We want to get the actions. We don't really care about the log probs at this stage. And then we just go ahead and return actions 0, because the tensor, I believe, is the output, and we want to return a NumPy array because the environment doesn't accept a TensorFlow tensor as input to the step function. So this is a simple interface function between the agent and its memory. And this is necessary because you don't want to directly access the values of the memory class from the agent class. It's just bad software design. You don't want to go overriding parameters of one class within another. You want to have an interface function that handles all of that for you, where you use one function to call another. That's just clean software design. Always keep that in mind. That takes a state, action, reward, new state. And it looks kind of silly. We could get away with it in this context because we're not going to be building on this code base later, but I always find it important to use strong and consistent software design principles wherever possible. Our update network parameters function is pretty straightforward. So we're going to pass in a tau, which is a default value of none. So if tau is none, then we want to go ahead and use our default value for tau. And this has to do with the fact that up here on line 153, we're calling update network parameters with the value of tau equals 1 to facilitate the hard network weight copy. So we're basically going to just go ahead and iterate over our network weights, do the calculation, append those to a list, and then upload that list to our target value network. Weight times tau plus targets times 1 minus tau. I have one too many parentheses there. That looks right. Set weights. And that is it for our update network parameters. Pretty straightforward. Next, we have two bookkeeping functions to save our models. Those don't take any inputs. Surveying. That is not useful information. So we just want to save the weights to the checkpoint file. Check pint. I'll take a pint. That sounds pretty good. And then the load models function is basically the inverse. So I'm just going to go ahead and yank and paste, and then make sure to change save to load. So that way we don't do anything wonky. actor.save weights, we want to change to load weights. And same deal, we want to load from the checkpoint files. Okay, now we come to the hard part of the problem, the learn function. Now we've got a kitty cat joining us. Perhaps she will hop up on the desk. The first consideration we have, is what we do in the event that we haven't filled up enough of our memories to actually load a batch size of those memories. And you can do many different things. You can play batch size of transitions randomly and store those transitions and then call your learn function. Or in this case, you can just say, hey, if I haven't filled up at least batch size of memories, just go ahead and return. So that's what we're going to do. And this is this violates my principles of good software design, where I'm calling the mem counter of the memory class directly here instead of using a function to get it. This is bad design. So don't do this if you have an option not to. I'm just doing this because it's, like I said, it's not going to matter. This isn't a huge code base that we're going to be building upon later, but just know that this isn't consistent with what I said earlier. I'm kind of backpedaling a little bit. Now we have to sample our memory. And we got to pass in our batch size. Then we want to go ahead and convert those to tensors. And I want to be really consistent with my data types here. Reason being, a lot of these frameworks, TensorFlow and PyTorch specifically, get a little bit finicky when you start mixing up data types. They don't like to mix data types in calculations because that screws up the precision of the calculation. They want everything to be consistent and explicit so that you get exactly what you expect, because of course there is a rather significant difference in large calculations between floating point 32, floating point 64, even floating point 16 calculations. So it's very beneficial to go ahead and specify what data type you're using. In this case, we use float 32. And we even, in theory, could get away with sorry, these are TF, not NP. We could get away with 16-point precision, 16-bit precision, excuse me, because we don't need, a whole bunch of decimal places in our rewards or anything like that. But we'll use 32 just to be safe. So now we're going to handle the update rule for our value network. So we need our gradient tape. So we're going to pass the states through our network and then squeeze to get rid of that batch dimensionality. Then we're going to do the same thing with our new states, except we're going to pass through the target value network. Squeeze again. What are the actions occurring according to our current policy and the log probs? So we're going to have to sample normal states, and we of course don't do any reparameterization. So then our log probs we have to squeeze. Then we get the values according to the new policy. Critic 1 states policy actions, and then the value according to the second critic. Then our critic value, not value, tf.squeeze, tf math minimum between the Q1 new policy, Q2 new policy. and I'm missing a parenthesis there. There we go. Now we're going to squeeze it along the first dimension. So then our value target is going to be our critic value minus our log probs. That's from the paper. Value loss 1/2 keras losses dot mean squared error between the value and the target value. Value target, sorry. Sorry, my toddler's rampaging again. So now we need to calculate our gradient. Good grief. I have the cat on my lap as well. That's making it very difficult to type. Value loss self.value.trainable variables. And we can stick that on a new line to be good little programmers. Then we have to apply our gradients. Optimizer.apply gradients, zip value network gradient, value trainable variables. And this is just how we do gradient descent using the gradient tape. And so that is it for our value network loss. Now we have our actor network and critic networks to worry about. So we need more gradient tapes. So we need our new policy actions and their log probs. We want to sample our states. Oh, that's interesting. I see. That's interesting. In my cheat sheet here, I have the NumPy arrays, and it works. Interesting. I'll go ahead and fix that. So let's see if it breaks when I pass in the TensorFlow tensors. It shouldn't. I just have a typo in my cheat sheet. So let's go ahead and squeeze our log probs and get some new policy values. Dot critic 1 new policy actions q2 new policy then we have our critic value squeeze math minimum. Then our actor loss, just the log probs minus that critic value. Actor loss equals math reduce mean actor loss. And then we have our actor network gradient, tape gradient, actor loss. The gradient of our loss with respect to our actor trainable variables. Then we want to apply our gradients, actor, optimizer, and of course that expects a zip as input. And that handles our actor loss. And finally we come to the critic loss. Now we have to pass the persistent equal true parameter to our function call because the loss is going to have two components. So we'll have a critic 1 and critic 2 loss. If you don't pass the persistent equals true flag, it only keeps track of stuff for the application of a single set of gradients. So you can only do the update to one of your critic networks instead of both. So you tell it to just keep track of the gradients even after it even after it applies gradients one time, so you can apply gradients twice. Our Q hat is our scale factor and multiplied by our reward. That's where the entropy comes in. Gamma times value underscore 1 minus done. That is interesting. So this gives me a little bit of pause because first of all, I know the code works. I've tested this and I haven't accidentally deleted a line. But what gives me pause here is that I have this value underscore, which is defined up in this other scope here. I'm actually missing a equal sign there. That would have triggered an error. So it does work. That's interesting. I didn't know that the context manager shared the scoping of variables. I didn't know that. That is new information to me. So I'm going to go ahead and roll with it for now. If this is suddenly broken and doesn't work, then I will come back and re-edit this and put in the new code that actually works, of course. But that is new information to me. See, I learned stuff even while making content. So we have to get the values according to the old policy. Why do I call it old policy? Perhaps go ahead and check the GitHub for this when I upload it. I will probably do some variable name swapping to make things a little bit more logical. If I have to scratch my head while I'm typing out the code here, you're probably scratching your head watching it. Of course, the losses are pretty straightforward, just mean squared error between the Q1 and Q2 old policies and this Q hat value. Then we can go ahead and calculate our gradients. Critical network gradient. So then we want to go ahead and apply our gradients. Sorry, Soft Actor Critic to network gradient, critic to trainable variables. And then we want to call our update network parameters function after we've done all of our updates. Okay, so that wraps up all of the heavy lifting for our code. Now we can move on to coding up the main loop, which is going to be a cakewalk by comparison. And of course I have an invalid syntax error. Oh, that's easy. There's no self there. Actions blank equals, and I've done it yet again. Oh, because it's a, sorry, my cat wants to steal the limelight. There we go. I did the same thing here, of course. Why wouldn't I do the same thing there? I like to be consistent. Okay, so now we're going to handle the main function. So of course we will need our PyBullet envs because we're going to be dealing with the inverted pendulum bullet environment. We need our gym, we need numpy, we need our agent, we need our plot learning curve, and that is it. I'm going to make our environment inverted pendulum bullet env v0. We need to make our agent. Pass in all of our relevant parameters. We'll play 250 games. Our figure file is just the directory plus the file name. You can condense that into one line if you want. It's not a problem. We say best score and the reward range 0. Score history, we want to keep track of the scores the agent receives over time so we can see if it's learning, as well as to plot them later. And a load checkpoint variable, which you can set to false if you want to load a checkpoint. So if we're going to load the checkpoint, I'm going to load your models. And one thing I like to do is set the render mode to human so that way you can see the agent play the game, because if you're loading a checkpoint, you probably want to evaluate the performance. If not, just comment out this line. In other words, if you're doing checkpointing so that you can do more training later, then just get rid of that line. No big deal. So let's go ahead and play our games. Reset your environment at the top of every episode. Reset your done flag. And set your score to 0. Play your episode by choosing an action. Take your action, get the new state, reward, done, and debug info back from the environment. Keep track of your score. Remember your transition. Not load checkpoint. Then you want to learn. The logic here being that if you're loading a checkpoint, you're probably evaluating. If it's the case that you're just loading a checkpoint to perform more training later, then you're going to need to put that agent.learn outside of that if statement. Just get rid of the if statement, okay? So that you're going to do what you actually intend. No matter what, you need to set the current state to the new state. And at the end of the episode, you want to append the score to the score history. Calculate an average of the previous 100 games. If that average score is better than your best score, then set the best score to that average so that you know you're learning. And again, if not load checkpoint, agent.save models. And you want to print episode I score average score, and then when all the games are over, go ahead and plot your learning curve. Okay, moment of truth. Let's see how many typos I made. That's easy. Plog. Replay buffer has attribute new size. It should be mem size. Self dot new size. I didn't do that elsewhere, I don't think. Okay, did I not call it call? That is interesting. So that is for my value network. Okay, replay buffer, critic, and value network. Oh, There we go. Sorry about that. Indentation error. As no attribute sample. That's because it is sample normal. That is in line 223. Agent.sample normal. Persistent, because I forgot a T, that is in line 239. Persistent equals true. That's another typo. Perfect. Eager ops is not callable. Let's see. Self.gamma times value underscore. Oh, I'm missing a multiplication sign. That is in line 240. Sorry about that. Line 240. 1 minus done. Good grief. Critic 1 underscore. That is in line 251. Oh, because it's not, there's no self in there. Okay. Good grief. There is no self there. Yep. Okay. Gradients do not exist for one of my layers. Okay. Means I have forgotten something indeed. That's problematic because it doesn't tell me, well, these warnings here, don't worry about those. Those aren't a problem. This gradient does not exist is in fact a problem. So let me see. I don't even know which network it is talking about there. It doesn't tell me. It says dense kernel 0. So that's probably whichever network I made first. So I instantiate my actor network first. So here is value actor loss. Let's check out our handy dandy cheat sheet here. And so I have located the source of the issue, and I will annotate this when I edit the video. But the issue here is that I was passing the state through both the first fully connected and second fully connected layer instead of allowing the output of the first fully connected layer to feed into the second layer. So, of course, that's how deep neural networks work, and you won't get anything useful if you don't feed things through properly. So let's go ahead and try it again. Okay, so now we got the same warning, and that's not concerning. It just has to do with the precision. So that's something you can deal with on your own if you want. I'm not going to go changing the backend settings. I could suppress the warning, but it doesn't really bother me that much. So I'm going to come back in a few minutes and make sure that this is learning. And when I do, I'll go ahead and show you the output of a fully trained network. And if it doesn't learn, then I'm going to go back and debug it, and you'll know because I'll tell you in a few minutes from your perspective. Okay, so here we are, and it's just a few minutes later. By game 60, we can see that the average score is improving with each episode, meaning that it is in fact learning, and it's getting well over 100. And so I'm going to switch to the other terminal where I have finished running it. I'm not going to wait for it to play all 250 games because it does take quite a while once it gets closer to 1,000 steps. So hold on one moment. So here is the output of an earlier model I trained. And I'm just checking the other window to make sure it is indeed still learning, and it is. It's saving models pretty much with every game. So this is an output of a model I ran earlier, where you can see that for the last several games it gets a consistent score of 1,000 with a little bit of a low flyer here at 751, still a respectable score. It doesn't have 100 games of 1,000, so the average score hasn't hit 1,000, but it is trending well up on its way. So I consider that to be a fully trained model. If it ran another 50 games, 100 games, then the average score would be 100 and we would have beaten the environment. So that is Soft Actor Critic in TensorFlow2. I left out the reparameterization because I don't think it's entirely necessary. I don't know why it was put in the original paper. I have implemented it in PyTorch. You can see that video if you want to see how that works. It's just passing in a parameter to your sample function, and if that parameter is true, then you use the R sample instead of the sample function from your distribution. If you want to implement that in TensorFlow2, I'll leave that as an exercise to the viewer, but you would have to do some simple calculation of adding in some spherically sampled noise to it. So that's not, it's not particularly difficult. It's just something I didn't want to bother with. So this agent learn, that is Soft Actor Critic in TensorFlow2, an incredibly powerful algorithm, indeed state of the art. I prefer TD3. I think it tends to perform a little bit better, but this is certainly no slouch in and of itself. I hope that was helpful. Leave a comment, a question, a subscribe, certainly if you've made it this far, and I will see you in the next video.